Hey guys, and welcome back to the channel. This is going to be a long one, so grab some popcorn, get a blanket, and sit down. Let's get ready for the ride. I am going to be doing the same, because as you all know, I hate to actually edit my footage, so I'm going to try and one take this, which means it is going to take me an absolute while. So a couple of quick announcements. First off, thank you to Ricardo, one of my viewers who has at least partially accredited me with helping him get some awesome staff offers. He's going to end up at Stripe, so congrats to you, dude. Genuinely amazing job. And to all the viewers who he has basically helped get over here via his Reddit post, welcome to the channel. Hopefully you'll enjoy this. So today we're going to be covering Uber. So as I often do when covering a video, I do my best to actually go ahead and look up a bunch of content about it beforehand. Just random blog posts as well as other YouTube videos. Even though I've made this one before, I mostly just reference what I've done in the past because I don't want to redo work, but I always try to check if I missed something. So I found some video on making Uber that covers it in 16 minutes and it has 600,000 views. And I'm sitting here thinking to myself, wow, I'm about to cover probably like 5% of Uber in an hour if I'm lucky. And wow, I get why Ricardo is saying this goes a little bit more in depth than other channels. Anyways, guys, let's go ahead and get into it. I want to go to bed soon enough, so don't want to take too long here. I'm going to do my best. Alrighty, let's go ahead and get into this thing. So for those of you who are not familiar, maybe you don't have Uber in your country, though I do think it is pretty global at this point. Uber is pretty simple. I want a car, I get a car, it takes me to where I want to go. So for example, if Kate Upton were to come to me and tell me to come over, I ask her why that actually is. She says, just do it, I have a surprise for you. Obviously, I'm going to come over there. Who knows what the surprise is, but there's not any chance in the world that I'm going to say no. So obviously, I'm off to Kate Upton's house, and Uber is going to show me where I am on the map, where she is on the map. It's going to show me the route to get there. It's going to show me the nearby cars in my area, and then it is going to help me match with a driver in order to take me there. So for those of you who have been around on this channel long enough to have seen my Uber 1.0 video, you'll know that I actually covered Google Maps in this video as well. I bunched them together. I'm actually not going to do this time around. The reason being that I want to go into a lot more depth in these 2.0 series. And if I'm going to do that, it means that probably Google Maps deserves its own 30 minutes at least, and so does Uber. So in this particular video, I am going to be attempting to cover the following. One is going to be literally just requesting a ride. How do we see drivers near us? How do we actually match with them? So that is going to be point number 2. Point number 3 is that we want to be able to provide some amount of distance that we are away from our location that we want to go to, and also the amount of time that the ride will take. So the thing with number 3 is this is pretty much all provided by some sort of mapping service. And like I mentioned, I want to make a dedicated video to this. So I will do that in a couple of weeks. I'm not going to cover this directly right now. For now, let's assume that we can abstract this all away into some third-party service, which I'll call Google Maps. And then eventually we'll talk about how we would actually go ahead and make that. And then number 4 is we have to actually compute the exact route that we are taking as we're taking it. This is good in terms of analytics purposes for Uber. It's good in terms of giving GPS instructions for what turn a driver should take. It's good in terms of knowing how much the ride actually costs as opposed to just estimations. This is an important thing. And it's not so easy actually because the GPS signal coming from your phone is not perfectly precise. It might be unclear which road you're actually on. So this is actually going to get complicated. I'm not sure if someone in an actual interview will ask you about part 4 of this question, but I actually think it's a very cool extension of this problem, and I definitely do think it is a hard problem as well. So let's start moving on. I'm going to do some extremely crude capacity estimates here, which again, I'm not aiming to be that accurate. My whole idea here is I just want to get the order of magnitude right. I might not even be correct on the order of magnitude. I might be a couple off, but I hope at least that these calculations will give us an estimate of, whether we need to do things like partitioning or replication or anything like that. So let's imagine that everyone in the world is using Uber and that everyone in the world is taking one 20-minute ride per week. So if a ride is 20 minutes, that means there are around 500 ride slots per week, right? Like if I'm a driver and I'm working all 24 hours of the week, I can service around 500 rides if each one takes about 20 minutes. So if there are about 10 billion people in the world, if there are 500 slots that a person could, take per week in their Uber ride, that means that there are going to be on average around 20 million rides at a time. Now again, I mentioned these calculations are going to be very crude. I think you can get away with this in an interview, but you can refine these if you want. So again, if we want to be able to say, if I'm a rider and I'm a driver and I want to map all the locations in our service, we have to keep track of where everyone is. There are going to be 40 million people at a time to map, right? The 20 million riders, and if we're assuming a 1-to-1 ratio of riders to drivers, then also another 20 million drivers. So let's imagine now that we're mapping people by their latitude, their longitude, and each one of those can be mapped with a 64 bit long. I wrote bytes here, but it actually meant bits, so it's really 8 bytes. Sorry, bits and bits, and then also that 64-bit ID. Okay, so if we multiply those all together, it comes out to around a gigabyte of storage, which is actually not a lot at all if we want to just go ahead and store the locations of all the people that are active in our system. However, we do actually have a problem here, which is that we're going to be constantly updating these locations, right? From the second I request a ride and from the second that I'm actually in a ride, I basically am constantly telling the servers where it is that I'm going. And so even if the storage itself is not a lot, there's going to be a ton of network requests being made. And if I'm just thinking about the number of ride requests being made, right, not even the number of location updates, if I'm assuming that there are 20 million ride requests per 20 minutes, that means that equates to around 15,000 requests per second. You can do the math there. And that is going to be a lot, right? Most servers are not going to be able to handle 15,000 requests per second. We're going to need to do some amount of partitioning just to handle all of that network data. Cool, so we've gotten that out of the way, and now we can start touching upon the first part of the problem, which is going to be actually finding a ride. So, I hate to say this to you guys if this is the first time watching my channel, but there is actually a couple of prerequisites to this video. The main one being the Yelp video that I just did last week. So in that Yelp video, I described the process of running a database query to find all points near you, right? So if I'm at a certain point in a map and I basically want to find all the points that are nearby me, I need a special type of database index to do so. Using a normal index, which could be indexed first on our X position and then within an X position would be indexed on our Y position, is not very efficient, right? Because I can say, hey, all right, if my point is here that I'm looking for and I want to find everything within this radius, well, first I have to go find everything within this X radius, which I can do. And then because you can only sort on one field at a time and then do inner sorts, for every X index, I now do know exactly where the Y points are that I want to get. However, that doesn't really help me because now, as opposed to being able to have all of these points that I want co-located within the database, they can actually be spread out all over the place, right? So, I could have X, Y, and maybe I want these 3 points, but then these guys are garbage, and then these guys are good, and then these guys are garbage. And ideally, for range queries, we want good data locality on disk, otherwise the whole thing is going to be slow. And so just a normal index is not going to work as well for us. Again, I recommend that you watch the geo-indexing video that I've posted if you're more curious about this, but hopefully that explanation was decent enough. The other option, of course, as I alluded to, is using a geospatial index. So in a geospatial index, we basically take our 2D plane and we break it down into a bunch of different bounding boxes. So in fact, we actually have bounding boxes. So this bounding box would be the A box, and then we have inner bounding boxes. So as you can see, I can now break this bounding box into 4 pieces. And then this would be the AA box, the AB box, the AC box, and the AD box. And we could even break those into tinier pieces, right? This would be ACA, ACB, ACC, ACD. And so basically by breaking down our 2D plane into a bunch of different bounding boxes, we can actually just search within a box in order to find all the points that are relevant to us, right? So if I'm looking to find all the points near this guy here, as you can see, the majority of them are going to lie within box BC. I know that, if I'm at the top right of box BC, that a couple of the points could lie in box BA, maybe even possible that some of them would lie in box BD. And then so I can search for all of those. But the main thing with a geospatial index that makes it so useful is that when I actually lay out all of the geospatial hashes, right? So all of these points have a hash, right? So let's imagine this target point right here is something like, I don't know, B, C, D, A, B. Keep in mind that I'm now laying out a bunch of other points on disk. And so all of the points that are close to me in 2D coordinate space are going to be directly next to me on disk. And so again, we achieve that data locality that we care about. We can do a binary search around this area, and as a result, we can quickly find all of the points that are close. Great. Hopefully that makes sense. So that's step one of finding a ride, is literally understanding how a geospatial index works. Step two is that we need to keep it updated, right? If I am at a certain point in our geospatial index, every couple of seconds I'm moving around if I'm a driver, and if I'm a rider, I could be even moving around a little bit as well. And so we have to send updates to that index to actually tell them where we now are. So of course we could send these via a normal HTTP request, right, and make a post to our server. However, there is one slight issue with that, which is that HTTP requests require sending headers, and if we're going to do this thing every couple of seconds anyway, it would be great if we just didn't have to send those. So what technology could help us out here is something known as WebSockets. WebSockets are a real-time bidirectional connection between the server and the client. And of course, this is going to be very useful for us because in addition to actually sending out our updates to the server, we can now actually see where other drivers on that same server are located. Cool, so hopefully that makes sense. So step three is, again, like I mentioned before during the capacity estimate stage, even though our index doesn't actually get a ton of data, it is going to get a ton of different requests from all the users and drivers that are updating their locations. So we're going to probably have to partition this thing out to make sure that every single partition gets an even amount of load in terms of the number of requests being made. And so if you watch my Yelp video, you'll recall that, of course, when it comes to geolocation data, we have to be smart, right? Because geolocation load is not spread out evenly. In major cities, such as New York City over here, there's going to be a lot more load per square foot than there is in something like Middle America. Oops, accidental erase. So again, we have to be smart about the way that we partition our data. In addition, we also need it to be the case that all locations that are close by to one another are on the same partition, right? If I'm a rider, I want it to be the case that all drivers that are close to me are on my partition, because otherwise if I wanted to search for all close drivers, I would have to hit a bunch of different partitions, and that would be bad. So again, basically the idea here is that we want similar locations to have similar geohashes. We're already doing this as a result of our geospatial index, and they should be on the same node. And of course, this basically just means that we want to be doing partitioning by our geohash range, but in a way that actually balances them so that all of the partitions get similar amounts of load. So we discussed how we could actually do that a bit in the Yelp video. I would recommend looking at that, but basically it does unfortunately involve a lot of tinkering. There are a lot of third-party services that can help you do this, but yeah, it's certainly not an easy process and is a video within itself. So let's actually go ahead and continue talking about this partitioning, right? So again, even if there are some partitions that cover really small amounts of area, they can still get too much load, right? If I'm in Times Square, which is a part of New York City, on New Year's Eve, which is where the ball drops, so it's super duper crowded, what you're going to see is tons and tons of people requesting Ubers home, let's say right after midnight, right? Everyone lets the ball drop, they're all tired, they want to go home. I personally stay out till 5 a.m. like a beast, but others, they do their own thing. So for these situations, what you can actually have is within a particular geographic area, you can even do a secondary shard on that, and you can just shard based on user ID, right? So even though all of these guys correspond to that area for Times Square, this is like user ID A through E, and this is user ID E through, I don't know, what's 2/3 through the alphabet, P, and then Q through Z. I don't know English, evidently. Anyways, the point is, even though I said this was kind of the range, this should be the range on the hash of the username so that they are distributed equally. Anyways, the idea is, of course, to first route the request by the geohash, and then from there, if there are multiple different leader nodes that this request can go to, you would then look at the user ID and perform an additional round of hashing to figure out where the request is actually going to go. And this is definitely something that Uber actually does. When I was doing research, it turns out that particularly by the San Francisco airport, of all places, there is tons of traffic, and as a result, they have multiple different replicas basically allowing you to match with drivers, which is pretty cool. So step 4, after we've done all of this, is that as we move from one area to another, this is especially relevant for drivers, they're actually going to have to change which partition they're connecting to. And if you recall, what we were previously connected to our last partition with was a WebSocket, and that's a little bit problematic because that is a persistent connection. So recall, the idea here is, we've got some load balancer, right? That's going to say, if I send you my location, you're going to have to connect me to a given server that is going to show where my location is. And so first I'm going to do that, obviously, because that is going to tell me like, hey, if step 1 is go to the load balancer is going to say step 2 is connect to partition 1, because that is where you're currently located. However, if I then send another message, right, and I establish my WebSocket, so I now tell partition 1, I'm actually over in partition 2, what partition 1 needs to do is break this connection, because then our client can go ahead and say, shoot, I don't have a connection anymore. I need to go back to the load balancer. So it's now, for step 3, going to go back to the load balancer. The load balancer is going to say, hey, wait a second, you're actually in partition 2 now. And now all of a sudden, you're making a WebSocket with this guy. You don't have this guy anymore. So the one thing to note there is we do want to be careful of the thundering herd problem. Namely, when you are reconnecting via WebSocket, you don't want a ton of different nodes reconnecting to this guy P2 at once, but it probably won't happen because it's not like everyone is leaving partition 1 at once and going into partition 2. Okay, now let's actually go ahead and talk about finding a ride. So the first thing is this: we want the reads and writes of the rider and the driver location to be as fast as possible. The reason being that they're happening every few seconds. We don't want them to themselves take a couple of seconds, or else we would be overloading our servers. Another thing to note is we don't really care if data is persistent, right? If I'm a rider and my location is in some sort of server, if for whatever reason that server goes down or it gets lost or something, it gets deleted, it's not a huge deal because I'm actually about to upload my information to the server in another 3 seconds. I don't really care about data persistence. I care about data speed and low latency. So ideally, we would keep our whole partitioned geolocation index on our servers, in memory in fact, because that's going to make things even faster. If we neglect to use a database here, which is what I'm saying we ought to do, not only do we not have to make an extra network call, so it's just client write to server, right? There's no database over here. Terrible drawing, don't have any of this. And also if we're just keeping everything in memory, because there's not a lot of things to store, like I mentioned, it's only like a gigabyte to store it. So we can easily keep it in memory in a pretty inexpensive manner. So let's just go ahead and do that. Okay, number 2 is that if a node goes down, we can basically just assign a standby node to its partition. So I'm proposing that we've got a few unused servers right here. So if for whatever reason this guy goes down, it's communicating with some sort of zookeeper instance, which in reality is distributed consensus. So there's 3 nodes over here. They're all talking to one another, 2 and 3. And then eventually they decide amongst the 3 of them that this guy is in fact down, and now they can say, oh wait, but this guy is up. Let's go ahead and actually promote him. So now all of a sudden, this standby node is going to take the partition of the dead node, and now our client is communicating with that guy. So keep in mind though that if this guy goes down, and if this guy gets promoted, now we have a bunch of clients who are starting to try to establish WebSocket connections with it, which could turn into a thundering herd. So the way that you would stop that, right, of all the clients, right, because if I have this guy over here and this guy over here, they're also going to attempt to establish webhooks at the same time, or rather WebSockets. And the way that we can stop this is just by saying, well, if this guy goes down, you wait 10 seconds, you wait 5 seconds, you wait 3 seconds, and that's going to distribute things a little bit. Cool, so now let's actually talk about picking a driver. So the first thing to note is there are a variety of different heuristics that you can use to pick a driver. I'm not going to enforce for the sake of the interview that you use one of them, but I think it's worth noting that there are different options. So first is closest, right? You literally go in your geolocation index and you pick the guy that's closest to you. That's pretty easy. Number 2 is you send it to everyone, and the first person to respond saying, yes, I accept this ride, is going to win. The next one is the highest rating wins. This obviously would, of course, require us having a driver's actual review score in the geo index itself. So now we have to store a little bit more data. So there's a slight downside there, but it's not a huge deal. But also another downside of this one is that you actually have to fetch everyone who's relatively close and then sort them by their review score. So that's a little bit of extra latency when actually requesting a ride. So there are a few different approaches of actually doing this, but all of them have in common that there are race conditions possible, right? Because even if you do pick the closest guy can still reject your offer. And so we do have to have the ability to, go and send to the second closest. And so whenever you have something like this, where, you provide an opportunity to one driver, and then if that doesn't work out, you provide an opportunity to another driver, there are plenty of opportunities for race conditions. So let's see how that might happen. Well, number one is the server looks for the closest driver, right? So it finds one, it's this guy over here, and it says, hey, do you accept this ride? Now what's going to happen is he actually does accept the ride. However, it takes 5 seconds for that network request to get back to the server, right? The response is unbounded in terms of how much time it can take, and as a result, we never know when the response is coming in. So as a result, the server 5 seconds later says, you know what, it doesn't seem like this guy has responded. Let me go and send it to this guy, number 2. Now he's going to accept, right, as the third thing that happens, and so this is actually going to get back to the server before number 4. And so now driver number 2 thinks he has ride. Blah, blah, blah. So the driver number 2 now thinks he has the ride. He's been told by the database, hey, actually no one else has claimed this yet. You're good to go. And then all of a sudden, this guy comes back in, claims the ride, and now they both think they have the ride. And that would be very bad. So in order to actually conclusively make sure that no one ever thinks they have the ride at another time, we need some sort of locking mechanism, right? So imagine we have some database table called claimed trips, where a trip first starts out as an unclaimed trip, and then it becomes a claimed trip when a driver gets assigned to it. Basically, this is when a rider asks the server for a driver, and so the first thing that the server does is assign an ID for that trip. And it doesn't have to put it in a database yet, it can do anything with it. But now the server has basically a couple of options. The first is it can actually materialize a conflict in the database. What does this mean? Well, effectively, it means you add a row to the database with an unclaimed trip, so no driver assigned, but it has the proper trip ID. So again, null driver, but has the trip ID. And the reason this is going to help us out is because now there's actually a row for us to lock on when claiming that trip, so that the drivers don't actually think that they both have it. If there wasn't a row there, it's possible that both of those drivers would just add the row, and if the row doesn't exist, we can't really lock on it, can we? Unless, of course, we were to use something called predicate locks, where predicate locks are effectively, it allows you to lock on rows that don't even actually exist yet by using something known as a predicate, which is effectively just a SQL query itself, right? So you could say lock all rows with a given trip ID. Of course, this is going to be slow unless our table is indexed by trip ID, because like I mentioned, the predicate lock is itself a query. And so we'd have to scan through the whole table of trip IDs, and that's going to be pretty slow. That's linear time, and that's bad if there are a lot of trips. But of course, if this guy is actually indexed and sorted, that sort time, or rather the query time, becomes O of log n, where n is the number of rows in the table. We can quickly find our trip ID, and then we're good to go. So that is a solid option. Now, of course, these are all techniques that databases use in order to ensure full serializability. Of course, we could also just use a database that supports transactions, which is what I personally would opt to do. I think using something like a MySQL database, which is just, sharded and partitioned, or not sharded and partitioned, but sharded and indexed on trip ID itself, is going to be sufficient here, right? Because again, we can easily perform that predicate locking or materialize the conflict, easy enough. If we're using transactions, we don't have to worry about any of this. And everyone's familiar enough with MySQL. We're not going to be creating that many of these rows at a time such that, writing or reading is probably going to be a bottleneck here. I think MySQL is probably good enough. Okay, so we've just finished the first part of the video. So that part of the video is probably what I would say that 90% of Uber systems design interviews are going to be concerned about, right? Creating that geolocation index, matching the driver, and I guess I've kind of brushed past it, partially just because the geolocation index itself is something that we talked about so much in Yelp. Now we have the super ultra balls to the walls, incredibly hard part of the problem, which I will dub route recreation. So this is one that's going to take a bit. You don't have to watch it, but if you do watch it, I promise it's pretty cool. Anyways, we're 23 minutes in. Let's keep going. So The idea here is that when we get a GPS signal from a phone, it's not perfect, right? So if I have 2 points on a road, we've got point A and point B, I might get a GPS signal that's actually kind of right in between them. And now I don't know where my car is. So the issue with that is that, we want to know our exact route. So what can we do to rectify this? Well, we can actually use some probabilistic models. So if I have this signal, I know for a fact that it's pretty unlikely that I'm at point C, and it's also pretty unlikely that I'm at point D because they're pretty far away. Additionally, if I first had a signal here and then I had one here, I know it's probably more likely that I'm at point B than point A because this guy is, over here on the road that leads to point B. So this is kind of the general idea that we're going to be getting into. We're going to be building ourselves a nice hidden Markov model, and we'll get all into that. So the first concept that I'm going to be talking about is called emission probabilities. And the idea here is basically, if I'm at a given location on the road, what is the distribution of GPS signals that might come from my phone, right? If I'm actually here over on point A, maybe it's very likely that I get signals over here, and it's less likely that I get signals over here, and it's not at all likely that I get signals over here. So we can actually model this with a math equation, which is what Uber does. I think they use the reverse Haversine distance or something like that. I'm no mathematician. Google it yourself. But the idea is an emission property is basically saying, if I were to see a certain point, what's the likelihood that my phone was actually over at point A? Cool. So hopefully that makes sense. You should notice that, if I were at B instead, there would be a different distribution of points that would be likely. I'd be really likely to see a GPS signal from here, less likely to see one from here, even less likely to see one from here, and I'm definitely not seeing one from here. Notice, however, that as we covered in the last example, that kind of radius of GPS signals that we might see could be shared in common for 2 different points. And that, of course, is when things are going to get a bit confusing. So the next thing that we're going to be talking about is something I already mentioned a little bit, known as transition probabilities. So this is basically saying, if I'm at one point on the road, what's the probability that the next place my car is going to be at is on this other point of the road, right? So from point A over here, maybe I have a model that tells me, oh, you know what? Because this guy is a highway, I'm really likely to stay on the highway and be at point E next. I'm a little bit less likely to get off the highway and go to point C. There's only a 30% shot of that. And just because point D is all the way over here and point B is all the way on the other side of the highway, there's a 0% chance that I can go from A over to one of those guys. So we can actually model these percentages by basically using historic data, by basically using certain heuristics like highways are more likely than like getting off a highway, things like that. And so now all of a sudden what we've done is built out this cool probability model. So let's go ahead and bring it together. Imagine I saw point 1 and point 2. So point 1 is over here, point 2 is over here between those radiuses of point C and point E. And so if I were to see that sequence, point 1 and point 2, what are the 2 points on the road that I was most likely at? Well, for starters, for point 1, we're pretty confident that we came from A, right? Because it's actually the only point, if I model B's distribution like this and D's like this, it's really the only point on the road where point 1 is in its circle. So I'm pretty confident I came from A, right? And if I know I came from A, then let's look at point 2. So point 2 might actually be a little bit closer to point C than point E, but even if it is, it probably doesn't matter. The reason being that if we're already at point A, it's so much more likely that we end up at point E than point C that the higher probability of being offset by point C is the higher probability of being emitted from point C is actually offset by the higher transition probability of going to point E. So hopefully that intuition makes a little bit of sense there, right? Like we're not just looking at this point 2, the GPS signal compared to other points on the road, but we're also looking at the trail of points that we've seen because the chain of them is actually going to tell us more information about where we actually are. So this is all, Bayesian probability, and it is encapsulated by a hidden Markov model. So again, if this gets a little bit too mathy for you, I don't blame you. It's not my cup of tea either, but for those of you who do enjoy the math, I'll devote one slide to it, and then hopefully we can go talk about algorithms from there. So let's imagine we modeled emission probabilities as this, right? So it's the probability that if I see a GPS signal, basically it's the probability that I see a GPS signal given I'm on a certain point in a road, right? So that's the emission. GPS signal 1 given I am at point A. So the transition probability is a little bit different. It's saying, I'm at basically probability I am at road 2 given I was at road 1. Hopefully that notation makes a little bit of sense so far. So if I were to see the signals GPS 1, then GPS 2, right? So imagine I'm seeing point 1 and point 2. That's what I'm modeling here. What's the probability of that? Really, it's very simple. All it is the probability that we see the signal GPS 1 given we're on road 1 times the probability that we are at road 2 given we were at road 1, right? So imagine this here. It's the probability that we see point 1 given we're at A times the probability that we're at E given we're at A, and then also times the probability that we see point 2 given we're at E. So hopefully that's simple enough. Now you might be saying to yourself, well, that alone isn't enough to know that it is the most likely sequence. We actually have to do that for all possible sequences of roads and then take the highest one, right? So take max. So for me to really be confident that I actually had the most likely sequence of roads, I would have to try this for, AB, AA, AC, AE, AD, and on and on and on and on and on. Even though these guys have zero probability for emission, if we really want to be sure that we haven't seen everything, we still have to try them, right? So the issue now is if we have X GPS signals that are emitted and we have Y different points on the road, there are going to be Y to the X combinations that we have to consider. Now, if you remember your lead code, anything that is exponential time complexity is a real no-go. It is going to take forever to compute, and ultimately just far too slow for us. So the question is, how can we actually go ahead and make this process faster? Well, for those of you who are still angry at lead code, I have a dynamic programming problem for you, and it is known as the Viterbi algorithm. So the Viterbi algorithm is actually a way of figuring out the answer to the most likely sequence given a hidden Markov model. And as opposed to running in exponential time, it is actually running in quadratic time relative to the number of roads in this case, and then linear relative to the number of signals. So this is a gigantic improvement in terms of the speed that we're running this thing. So let's actually go ahead and explain how it would work. So basically, the idea is this. For our first signal, let's keep going and thinking about that example that we were using just a couple of slides ago. For our first signal, we want to find the probability it is emitted by each road. So we just have our emission probability. We're not thinking about transitions yet. And then for the second signal and on, we basically use the previous results, right? We take the highest possible path from each node, and then we use it to calculate the most likely path ending at each node. So we go from each node, we have a probability there already, and then we use it to calculate the next set of probabilities for the next signal point. So I'm going to do my best to illustrate this. I'm not the best teacher, but let's see what I can do. So let's imagine now that basically, signal 1 comes in, forget what the emission probabilities are there, don't worry about it, and then signal 2 comes in. And so I say that, through signal 2, I see that if my car was at point A, and then it was at point A again, I would have a 1/4 probability of seeing the GPS signals that I've seen. If I have to look at all potential routes that end in AB, I would now have to say, okay, if my car was actually at A and then it was actually at B, I would have a 1/2 possibility of, basically there's a 1/2 chance that I would see these signals, right? So now the question is, what do I do for signal 3? So another signal comes in. And so the question is, basically, was I at AAA, AAB, ABA, or ABB? The reason I say that is because in the Viterbi algorithm, we actually only care about these points from our signal 2, and then we go and do another crossing between these guys, where, keep in mind, the crossing is basically, we take these possible signals, we multiply them all by their transition and their emission probabilities, and then at every single node you just take the max possible number. So let's see, to simplify things a little bit, in this case it would really be the max of AA times transition from A to B, and this guy would be the max, or rather just AB times transition from B to B. And the idea here is that, only these calculations alone are going to tell us the max possible path ending at B on the third signal. And so you might ask yourself, why is it basically that we can discount any of the other paths thus far? Why is it that BBB can't have the highest probability? Well, basically keep in mind that at every single step, we're really just taking the highest thing up to that point, and then we're multiplying by the transition probabilities regardless. And so if we're multiplying by the transition probability from here to here, if I know that BB was less than AB before, I know that, sorry, I'm running out of space here, BB times the transition probability is less than AB times the transition probability. And so as a result, again, we have found our dynamic programming use. We basically just need to memoize the calculation of the previous signal, and then we're good to go. If I didn't explain this well, I apologize. There's really one takeaway to get, which is this. As opposed to the naive algorithm of hidden Markov models, which in theory could be run in parallel, right? You just do this calculation for all combinations of roads in parallel. In the Viterbi algorithm, we need to run this thing sequentially. In order for me to calculate the best result for signal number 3, I need to know the result for signal number 2. So again, the point here is that this thing is stateful. We need to run it sequentially for signal x. I need to know the probabilities for signal x minus 1. And so, again, this is going to make our life a whole lot tougher, right? Because if we have to do all of this computation, it's a little bit complicated. It now means that as I send points coming in, those points have to be able to access the state of the previous node in order to do the next calculation. So the good thing for us is that this state isn't too big. So I did mention that in a Viterbi algorithm, in most hidden Markov models, you would have to consider every possible path, or at least all possible paths ending at one particular layer of nodes. However, for the majority of these roads, a lot of the paths are just going to have a 0 probability, right? Because some of the emission signals are going to be so far away from certain points at a road that we can actually just discount that whole node and then not even worry about it. So at least in my opinion, I think the state itself that we have to pass around from calculation to calculation will probably be pretty small. So again, probably only a few sequences of roads will actually make sense and have non-zero probabilities. Okay, so I've gone through all this math. That's been pretty useless thus far. And now it's actually time to get into the whole distributed systems aspect of this thing, because this is where it really gets fun. So here's the first thing we're going to say. Our hidden Markov model is big, right? There's a lot of data here. We're modeling the probability that every single road is potentially going to every single one of its neighbors. And again, that just takes a lot of data to do. And so because we have all of these transition probabilities, now all of a sudden we probably have to go ahead and make partitions, right? So that is going to be tough. So imagine we have the following scenario. Our car starts out in zone 1, which is going to represent one partition of our hidden Markov model. So P1 is going to hold all of the transition probabilities there. Then we go to S2, so same node, we're all good. right? We're still accessing the same data. And now all of a sudden we go into S3, which is now part of a different partition, right? This is part of zone 2. And so all of a sudden a different server is holding the transition probabilities that we need. So in theory, this wouldn't actually be that problematic if we could run all of these calculations in parallel. However, these calculations are stateful, and I need the result of this guy, right? I need the result of the calculation for S2 in order to perform the calculation for S3. And so now, all of a sudden, P1 might be holding the state from these two calculations, but now it has to actually go from P1 to P2. And so the question is, how does it actually get there? So basically, there are a couple of points that I'm going to talk about before we talk about how we can pass this state around over the network. The first is that we want to be partitioning our HMM, like I mentioned. And we're going to do this in a way very similar to our driver matching service, right? So the idea is that we want close points that are actually close to one another in space on the same partition, because if I'm moving around a little bit, it would be great if all of my queries to figure out the transition probabilities from one road to another were on the same node. And as a result, we want to basically partition our HMM in the same exact way that we did earlier, where, New York City gets a node, Middle America gets a node, et cetera, et cetera, et cetera. So there's one slight exception, right? Which is that imagine I'm moving first from point A here to point B, and A and B are basically going to be on different partitions. Now the issue with that is that I actually need to know the transition probability when I see point B. I need to basically know the transition probability from A to B. And I'm not going to have that if A is on a different zone, right? So now this is a different partition. So what we can actually do is, in order to ensure that all of the transition probabilities that we need are on our partition that we are querying, we can actually extend our HMM bounds a little bit, so that, for example, all of the HMM transition probabilities held on partition 2 are going to extend a little bit past the zone 2 boundary, right? It should end here, but it actually ends here. And we're going to do the same thing for P1, right? So it should end over here, but now it's actually going to end down here. And what this is going to allow us to do is, this query, right? If I see this GPS signal, this is going to be handled by P1. P1 needs to know, hey, what's the likelihood of A to B? We can see it's 80%, but that would normally be held over on P2. But if we just extend these bounds a little bit, now all of a sudden that 80% is also held on P1, and we can do our calculation. Again, I'm sorry if this is getting a little abstract, but hopefully the general idea makes sense here, which is that if I just cross a partition boundary, I need to know the transition probability across partitions, and it would be bad if we had to go to multiple nodes in order to figure that out. Okay, we're still dealing with partitions here, because again, this is all very complicated stuff, and even though it feels convoluted, this is actually kind of similar to what Uber really does. Who would have thought? So the idea is, again, we need to access our last computation, right? Not our last trip, but rather our last signal. So if I have signal 2, I need to know the computation from signal 1. And so the idea is, if we move partitions, we need to be able to fetch that state. So imagine signals 1 through 5 are all in P1. All of a sudden signal 6 comes along. That's now located in P2, right? It's just a different zone of the map. Now all of a sudden this guy needs the state from P1. It's got to ask it for it. Hey, can I have your state? It doesn't necessarily have to ask it for it, but there's got to be some sort of mechanism for actually passing that state around. So here is the way I'm going to be proposing to do it. Basically, I propose that when we pass a signal, like a GPS signal, to our partitions, like so, it should look something like this. It should contain trip ID, it should contain the previous location that the car was at before this one, so the last signal, and then also our current location. So this is going to allow us to accomplish a couple of things. The first is it also tells us when we're actually starting and stopping a trip, right? If the previous location is null, the current location is not equal null, then these servers know that we're actually starting a trip, which is useful because now they're going to have to start keeping track of state. Before, they might have said, oh shoot, we should have this state. Where is it? I might need it. Trip started. The next is, if the previous location was not null and the current location is null, we can basically say, okay, that means the trip is finished. let's take our route that we've calculated, the most likely one, we can upload it to some sort of trips database. And the idea here is that also this signal has all of the information that we actually need in order to deterministically figure out which partition this is going to, right? There should be some sort of load balancer here, and the load balancer, using all three of these fields, is going to be able to figure out where this message should go. It can take a geohash of our current location. If we're doing some inner sharding, again, because, think about the Times Square on New Year's example. If there are, if there's tons of load for a small given area, we may have to do some inner sharding within that. And then we could do an inner shard on our trip ID as well to figure out which particular replica our query is being sent to, right? So if I have, zone 1, replica 1, and then zone 1, replica 2, I basically need to figure out, using the trip ID, because I already know from my geohash that I'm going to zone 1, but using the trip ID, do I go here or do I go down here? And we want to keep that consistent, of course, and we'll explain that in a little bit. Okay, well actually, you know what, let's explain that now. Why do we want to, keep which node we're hitting consistent? Well, the reason, of course, is that we're maintaining this state from before. And so these guys are going to be stateful consumers. And so if, I'm non-deterministically hitting, this guy on one signal and then this guy, the state that I need is not going to be maintained. So I actually need, like Jordan's trip has to be on zone 1, replica 1. And if I go to a different zone, then I'm going to have to take Jordan's trip and I'm going to have to send it there. Okay, let's talk about inter-partition communication. I thought I was real clever for this one. It's possible that one of the senior engineers who watches my video is going to roast me, and I am open to such a thing. So, like I mentioned from before, the toughest thing about this whole problem is that cars can go from one zone to another. And when they do, you have to actually go ahead and move the data associated with that car, right? So the whole point of the Viterbi algorithm is that I need the result of the last computation. If the last computation is being stored on a stateful consumer for zone 1, now all of a sudden I have to send it to the stateful consumer for zone 2. So if you keep hearing the word stateful consumer, and you've watched enough of my videos, which many of you have, you know that I am a flink sexual. Apache should be paying me at this point. They can't because they're open source and they have no money, but if they could, they should be paying me. Anyways, the point is, what am I proposing? As per usual, I'm proposing using Kafka queues as well as Flink. The reason being that Kafka queues are basically a distributed log-based broker, so of course all of those messages are going to be persistent and replayable, and Flink is capable of keeping state and actually occasionally checkpointing it to ensure that all of those messages are eventually going to be processed at least once. So, how do I actually want to go ahead and convey Viterbi state between signals, right? So if I switch from zone 1 to zone 2, now all of a sudden I have to give the state from my Viterbi calculations from zone 1 to zone 2. How do I propose we do this? Well, basically, I'm saying that we should go ahead and actually send the trip Viterbi state to the Kafka queue for the new partition, right? So we're going to have zone 1 over here. We're going to have zone 2 over here. Zone 1 is going to say, wait a second, I see that the car is no longer in my partition. Let's go ahead and send it to Kafka. And then zone 2 can go ahead and consume that. We're going to now illustrate all of this because I have been so abstract and everyone is better learning visually. So let's go ahead and do it. So the idea here is as follows. I'm going to do my best to explain this. So imagine we have zone 1 is this box on my right, zone 2 is the other box on my right. As I mentioned, the actual partitions themselves for the hidden Markov model nodes, the stateful consumers, are going to be a little bit bigger than that, just so that we have all of the transition probabilities that we need. So like I mentioned, the data model that I want to use for sending signals is like such. We've got trip ID, previous location, new location, new location. So in this case, the previous location was null, the new location is going to be P1, and the trip ID is going to be 10. So the trip is going to start out in zone 1 at P1. And so the first thing that we're going to do is the client, right? This is really all the client that's sending all this data. Got my smartphone right here. my smartphone is going to send this guy over to the load balancer. And the load balancer is going to do the following. They're going to say, oh wow, the new location is P1. So let's actually go ahead and send this point over to the zone 1 queue. This is in Kafka. And this is now going to initiate holding state for my trip number 10, in the stateful consumer. The next thing that's going to happen is I'm going to move over to P2. My ride has gone south a little bit. And so now I'm going to send a message saying, hey, I was at P1 before. I'm now at P2. My trip ID is still 10. This goes to the load balancer. The load balancer says, oh, P2 is still in zone 1, which means I'm going to send you to the zone 1 queue. It's going to take a geohash to figure that out and use our custom partitioning logic. And again, this is now going to perform the Viterbi calculation, right? Because we have transition probabilities for zone 1. So it's going to perform that calculation, and now it's going to update the state for trip 10. Next thing that's going to happen is now all of a sudden we've actually moved into zone 2, and we've gone to point 3. At point 3, what's going to happen is we're still at trip 10. Our previous point was point 2. Now we're at point 3. So this is where things actually get a little bit interesting. When we get to our load balancer is going to say, oh, wait a second. I see our old point is in zone 1. I see our new point is in zone 2. I'm actually going to send this message to both of them. So zone 1 is going to get message number 3. Zone 2 is going to get point number 3. And so when zone 1 sees this, it says, oh, wait a second. I can see that now all of a sudden, basically this point is no longer in my zone that I'm responsible for. So now I have to actually take the state for this trip and send it back to my load balancer. And the load balancer is going to say, oh, wait a second. Well, I know about this because I can see that we're now currently at point 3, right? This guy knows that we're at point 3 now. And the load balancer is going to say, I'm going to have to reroute this to wherever point 3 lives, which is the zone 2 queue. So now the state from the zone 1 Flink consumer is going to go into the zone 2 Flink consumer. We can establish trip 10 state. And then once basically this state as well as this point have arrived, now point 3, we can now run Viterbi. Again, I'm sorry if you're not following along, doing my best here, but the idea is, we get our state from the previous calculation, we send it, we use our deterministic partitioning and load balancing algorithm to make sure that it goes to the right place, and now all of the data that we need is in one place. We're bringing our computation to the data, right? All of our transition probabilities live on zone 2, so we want to make sure that we're doing this calculation on zone 2. And then the last thing that we're going to do is we're going to move over to P4. The driver marks our trip as ended, so now all of a sudden we say, okay, our old state was P3, our new state is null. The load balancer is going to say, oh, if your old state was P3, that means I have to route this guy over to Z2, right, because we're in zone 2. So we're going to route point number 4 over to zone 2. And then all of a sudden, this guy is going to say, oh, wait, this is done. Let's go ahead and send this state to the trips database. And now we know our exact route, or at least the most likely one according to our hidden Markov model. Whew, that was a lot. Let's go ahead and outline this thing all at once. So we're going to start off with our client over here on the left. As we do whenever we're looking for a ride, the first thing that we're going to do is reach out to our load balancer, because all of a sudden we want to actually say where we are so we can start looking for nearby drivers. So the first thing that we're going to do is our load balancer is going to basically geohash our current location and match us with one of our nodes in our matching services. So let's say it matches us with this particular guy, right? This one is New York, and that's where I am. New York. So we establish a WebSocket connection with it, and now all of a sudden we're also consistently getting data about where the closest drivers are. So we've requested that ride. A driver is eventually going to also be connected to this guy. So this is our driver. And when he clicks accept, that's going to go into the trips database, right? Now all of a sudden our trip has actually been created. Both of us know about it. I hear about it through the WebSocket. He hears about it through just, getting a response from the matching service. So also as well through his WebSocket. And then we can both see one another's locations, again, via the matching service as he comes to me. I get in his car, he clicks, hey, the ride has started, and now all of a sudden, from our client, we're actually sending our locations during the ride so that we can calculate the path that we're taking. So this is going to be path calculation. So again, as we're actually sending out all of these GPS signals, right, trip ID, old location, new location, these are going to go into a load balancer, and the load balancer is going to place them into basically the correct Kafka queue, which again, we're going to be sharding on our geohash because we want all of our HMM nodes to be sharded by their location and balanced properly. And if we have to, again, think of the Times Square on New Year's Eve example or the San Francisco airport example. We may have to do some inner sharding on the actual trip ID itself. All of that can be accounted for deterministically in our load balancer. We can use some sort of consistent hashing function. So again, these guys are all going down over to our hidden Markov model nodes, which are going to be keeping state of the last Viterbi calculation that we've run. And then as a signal comes in again, it's going to run yet another Viterbi calculation. Of course, if all of a sudden, I was going here and now I've moved my car and I have to start doing Viterbi calculations on this node, this guy is going to have to send its state back to the load balancer, which is going to, again, route it through the Kafka queue. It's really beneficial that all of these messages are going through Kafka as opposed to using some other sort of transport protocol, because of the fact that anything that is running internally within Flink is guaranteed to eventually be delivered, right? So I know that all my state is going to be checkpointed or snapshotted, and I don't have to worry about nothing getting run. If I were to use just like a direct HTTP request between these two guys, there are a bunch of race conditions that I could spend a bunch of time thinking about and dealing with, and I would rather not. So I would rather just route them through Kafka. Now, of course, when the kind of like finish event comes along and this guy processes it, it's going to upload that data to the trips database. The trips database is, again, like I mentioned, a simple MySQL database sharded on the trip ID and indexed the same way. We can keep it single leader, so we've got this replica. And in fact, we also want the data from there to do some more post-processing on, right? So we can extract it via change data capture, as I've done many times before on this channel, throw that bad boy into a Kafka queue, put it into an HDFS sync, and then start running Spark jobs. The reason for this is we actually want to just get more transition probabilities. As we get more data over time, it would be very useful for us to figure out how likely it is that you go from one road to another. And so we can actually feed this data into something like a batch processing job that's going to make those probabilities more and more accurate. And then we can feed the result of that Spark job into our hidden Markov model nodes such that we get more accurate probabilities for transitions from one road to another. Well, guys, if you have followed along, I am incredibly impressed. I don't think I explained this one particularly well. However, I did do my best with some visualizations. I will make sure to attach an article in the description that I based quite a bit of the latter part of this video off of. But again, for those of you who are new to this channel, welcome. I'm excited to have you all here, and I'm looking forward to keep making these videos. So have a good night, everyone. I will certainly do the same, and I will see you in the next one.